Topic 8b, single variable optimization. So by single variable, we only have one independent variable, something like x, and we're trying to find either a maximum or a minimum as a function of x. What value of x leads to that minimum or maximum? Before we get into that, I want to cover some mathematical preliminaries about extrema, so minimums and maximums, first derivative test, second derivative test, those sorts of things, because we will use them when we talk about optimization. The remainder of this lecture is just talking about single variable optimization, and we'll talk about three different types. The first two are quite simple, and the third one will go into more detail, and it's pretty neat, I think you'll find. In the lecture following, we'll talk about multivariable optimization, and what you'll see is a lot of them are based on this lecture, a one-dimensional optimization, and we can talk a little bit in more generality when we get to 2D optimizations by saying stuff like we'll perform a 1D optimization in this direction, then another one in this direction, and we'll do something else. So the 2D optimizations is very often built on top of 1D optimizations. All right, so some mathematical preliminaries. We have the first derivative test, and the derivative is the slope of a function. So if a function has a maximum or a minimum, right on that maximum or minimum, that slope must go to 0. So this gives us one way to potentially find that minimum or maximum. The derivative has to be 0 there. It has to be 0 because the function itself has to turn around, and so it has to pass through 0 slope. Now the second derivative test, the second derivative is the slope of slope, or we can think of it as curvature, and we can use this to tell whether, once we've located an extrema, extrema is the generalized term for maxima or minima. So given that we found an extrema, we can tell whether it is a maximum or a minimum. If that second derivative is positive, we've found a maximum, and when it's negative, we found a minimum. And from our discussion of the merit function, we can formulate our merit function so that we're optimizing by either maximizing or minimizing that merit function. So which way you do that's really up to you, and all of these algorithms can usually be turned around to work just as well for finding minimums as maximums. But these derivative tests give us ways to find them and identify whether they are a minimum or a maximum. So our first optimization method is parabolic interpolation. I think you'll find this very easy and intuitive if you're comfortable with fitting polynomials to discrete points. So it's as simple as this. We have a smattering of points, usually 3 points. We fit it to a polynomial. Now we have a closed form equation that describes those 3 points. And we can take the derivative of that, set that equal to 0, find the value of x that maximizes that polynomial, and we're done. So let's step through that in a little bit more detail. So step 1, we have 3 points. Could be more than 3 points. The point is we really have some smattering of points that we fit to a polynomial. The assumption here is, though, that these are spanning some kind of extrema, that there is a minima or a maximum somewhere between these 3 points. So once we have those 3 points, the second step is then to fit it to a polynomial. And just to remind you, we write the equation for the polynomial once for each of our points. We put that set of equations in matrix form, and then we backward divide to find the polynomial coefficients. Once we do that, now we have a closed form expression for a function passing through those 3 points that we originally specified. And it's quite easy to find the extrema of a closed form expression. So on to the third step, and we will use the first derivative test to find the extrema. So we differentiate our polynomial to arrive at its derivative. We then set that derivative equal to 0 and solve for our value of x. That gives us where that extrema occurs. And if we wanted to, we could then apply the second derivative test to determine whether that extrema is a minimum or a maximum. Now, if we spend a lot of time on this and work through the algebra, we don't necessarily have to form these matrices and do all that work. Everything's boiled down into this one single equation here. So if you have a symbolic editor, you can go through this and it'll spit out that equation to find the extrema. So in practice, I would probably build the matrix, backward divide, and then say negative a1 over 2a, rather than type out this big, long, ugly equation. But in the end, that's the calculations that would happen anyway. So that's it. That's the polynomial method. Let's visualize what's happening here, though. So in this case, the blue line is the true function, and it's not exactly a polynomial. And the solid blue lines are our three discrete points. So since that isn't a polynomial, when we fit a polynomial to it, we get a slightly different function. So this dashed red line, that's the polynomial that we fit to that in those 3 points. If we then run the optimization, it puts the peak of that polynomial right here. Well, the true peak is over there, so there is some error here. And so, well, what if we wanted to reduce that error? Well, certainly the more closely we can space those points to where the extrema is, the more accurate we will be. And also, the more polynomial looking that original function is, the better a polynomial can approximate it. And we could imagine doing this with a third order polynomial or really other functions that might fit the true function better, where you can use that to find the extrema. So you could do a curve fit, maybe you do a nonlinear regression to fit a Gaussian to a set of data, and then you can find right where the maximum of the Gaussian is. So you can choose your function based on the physics of what you're analyzing, try to come up with something a bit more consistent. So just demonstrating here with a polynomial. On to Newton's method, not to be confused with the Newton-Raphson method that we talked about when we did root finding, but what you'll see is Newton's method is a small little twist to the Newton-Raphson method. So let's remember the Newton-Raphson method. That was when we were finding roots. We wanted to find values of x that forced our function f to 0. So given that function f and given its derivative, we derived an update equation. And we kept repeating that equation over and over and over until finally that value of x converged to wherever that root would be. And we looked at how quickly or how much it moved from iteration to iteration to control how accurate our answer was in the end. So that was the Newton-Raphson method. However, for finding extrema, we're not finding roots. We are finding minimums or maximums. So let's remember the first derivative test. The first derivative test says there's a maxima or minima where the derivative equals 0. So maybe to find an extrema for a function, rather than work on that function directly, let's work on the derivative. Let's do root finding on the function's derivative. And so that's what Newton's method is. We'll calculate an auxiliary function g, which is just the derivative of f, and perform root finding then on this auxiliary function. That's Newton's method. So Newton's method and Newton-Raphson method are almost the same thing. It's just that the Newton-Raphson operates on the function directly to find roots. Newton's method does the Newton-Raphson method on the derivative to find extrema. So we end up with an update equation now, where instead of the function, we're using g's, our auxiliary functions. And we can replace those with our original derivative. And so we would write the update equation this way. So we have the derivative of f in the numerator and the second derivative in the denominator. So the Newton's method is simply Newton-Raphson method, finding roots of the derivative instead of the function itself. So that's pretty neat. So knowing the Newton-Raphson method, it's a very quick thing now to teach you a whole new method. Now let's talk about the golden section search. I think you'll find this a pretty neat method, and we'll go into a bit more detail on this than the previous methods. So let's get started. Now this starts looking a little bit like the bracketing methods that we talked about for root finding, and there'll be a twist here, but it starts off the same way. We define an interval. We'll define a lower limit and an upper limit and make the assumption that somewhere between those limits, our function reaches an extrema. So for this example, we're finding a maximum of f, not a minimum of f. And I'll try to point out what you would do differently to find a minima versus a maxima. But the algorithm itself can do either, just with a simple little tweak. Okay, so we define our interval. That's step one. The next thing we'll want to do is evaluate the function at those endpoints. And to understand and appreciate why we want to minimize the number of times we evaluate that function, put yourself in the mindset of every time we evaluate the function at a value of x, it takes an hour. Maybe that's a simulation or something else. That puts you in a healthy mindset in our attempt to minimize the number of times we have to call that function. So here we called it twice, so we're doing 2 hours of computation, for example. So we evaluate the function at the bounds. At this point, and this seems like a weird step, later on we'll derive the math here, but we calculate two intermediate points, x1 and x2. And we do it in sort of a strange way. We're placing x2 as some distance from the lower limit. So x2, some distance from the lower limit. And we're looking at placing x1 some distance back from the upper limit. And both are coming from a distance d. And that seemed a little strange. And we calculate this distance d as this function r, or constant r, times the total span. And it turns out this value r is the very, very famous, known from antiquity, the golden ratio. So yes, that's the same golden ratio that Leonardo da Vinci put into his artwork and is all over the place. It's neat. Do a Google search for that and look up golden ratio, and it has a pretty cool history. So that's the number, and that's where it appears here. And later we'll derive it and explain why that's important here. But anyway, we calculate these two intermediate points using this golden ratio. Then we'll evaluate the function at those two intermediate points. So along the lines of our mindset of this taking a while, that's now 2 more hours of computation. So totally up to this point, 4 hours of computation, because we have 4 points and we had to evaluate the function at each of those. Now, in the remaining iterations, we really want to minimize how many times we call the function. And this is really the purpose of this golden ratio. Let's see how this works. Okay, so we've evaluated the function at these 4 points. Now we want to figure out really which side of this limit, where is that extrema? So let's think about how we identify that. Visually, we can see that it's to the right. But algorithmically, we just look at the values of f1 and f2. So we're looking at these two values. And if f1 is bigger than f2, the extrema will be on the left. Now in this case, we have f2 that's bigger than f1, so the extrema is to the right. So if we're looking at which one's bigger and moving to that side, we're finding a maximum. Now if we were finding a minimum, we would look at which one of those is smaller and realize that the minimum is on that side. But here in the context of finding the maximum, we're looking at which one's bigger. So f2 is bigger, and so we move our new interval now over to the right-hand side, and we eliminate this entire section of our original interval. And it turns out that's about just under 40% of the total span we've eliminated. And so now what we do is we close in on that. We move our limit in on that span we have highlighted in gray. Now something happened, we'll talk a little bit more, but we move our limits in, recalculate those intermediate points, and something sort of magical happened. Our lower limit moved up to a previous point. And unfortunately, I can't go back and forth in these slides because it'll erase what I'm saying right now. This point fell on a previous point. The upper limit didn't move, so that's on a previous point. We only have one new point here. So to get the function at our 4 points, we only have to evaluate the function at that new x2. And so therein lies really the magic of why we're using this golden ratio. We've adjusted our interval, but we only have one real new point to calculate. Now we compare f1 to f2. f1 is now the bigger value, so we know that the extrema happens to the left of f2, and we close in our interval on that. So we close in our interval, evaluate a new x1 and x2, and there's only one new point here. All the other points coincide the points from the previous iteration. And so here's sort of a freeze frame of a bunch of different iterations, and we can watch our lower and upper limit converge. And we can check those. If the lower and upper limit, if the change from iteration to iteration falls below some tolerance, we'll say that we're done. So in the end, our upper and lower limits are probably still some small distance apart. One thing you can do is just average them and say that's my final extrema. Another thing you could do is fit those to a polynomial and use the polynomial interpolation form of optimization to make that final last estimate of where the extrema would be. So you can imagine now combining different optimization methods. So this is just one and probably the easiest. So overall, here is the algorithm. So step 1, we define our bounds. Step 2, we evaluate the function at those bounds. Step 3, using the golden ratio, we calculate 2 intermediate points. Step 4, we evaluate the function at those 2 points. Step 5, we look at the function value at points 1 and 2. We figure out which is bigger or which is smaller if we're looking for the minima. But we figure out which is bigger, and we move our interval over to that side. And what you'll notice is that we're copying over a lot of information. We only have to evaluate the function at one new point. And depending which side we move to, it depends which information we copy over to what parameters. So we adjust our interval, and then we check the distance on step 6, and we see if we've converged. And if we've converged, we'll calculate our final answer, and we'll say that we're done, and we found an extrema. So that is the golden section search. Let's look a little bit more deeply at some details. So here's an animation that I put together, and watching this, you'll really see how the points from one iteration and the next iteration lie on top of each other. Let's go ahead and run it. So here's the start of this, where we have our limits and our 2 intermediate points. So we're going to the next iteration. So I just sort of slowly slide the new points, and you can see where they coincide with the old points. Those dashed vertical lines, that reminds us where the points were on the previous iteration. And what you can see is that the new points, 3 of those new points lie on 3 of the old points. There's only one new value. Let's go ahead and play this one more time. Remember, the dashed lines are our previous points. And in the next iteration, 3 of those line up. We don't have to reevaluate the function there because we already know it. So anyway, that's my little animation of the golden section search. Now let's derive the golden ratio in the context of this method. And so we lay out our upper lower limits, and we will define the total span between the upper and lower limit as L sub 0. And then we have an L1 and an L2. And so we can define our L's in terms of our X values here. Okay, so that's the first step in this. Now our real goal here is when we update and we move or we squeeze in our interval on one side or the other here, that the points overlie, our new points overlie on the old points, so we don't have to reevaluate the function. So we have some conditions, two conditions that'll turn out to ensure this. One, we need to make sure that our L0 covers the entire span. So L0 has to be L1 plus L2. Maybe that's kind of obvious. This next one maybe isn't so obvious, and we really have to look at our points before and after we've adjusted them to understand this. But the ratio of L1 to L0 has to be the same as the ratio of L2 to L1. That's the condition that ensures when we adjust our points that we overlie onto our old points, or at least 3 of them overlie. We only have one new one. So these are the two conditions that we have to ensure so that this golden section search can do its magical stuff. Okay, so up top we have a repeat of these two necessary conditions. So what we'll do is we'll take L2 plus L1 for L0 and substitute that in here. So that's what we have. So we've combined the two above equations. Now we're going to do some algebra on this. Let's define a constant r, and it turns out this is the golden ratio. Let's define that constant as L2 over L1. Well, what we'll do is we'll take this equation that has L2 and L1 and just do some algebra on it until we end up with a form that only has that ratio of L2 to L1. We can then replace those ratios with r, and then from that form a quadratic equation. So we can solve the quadratic equation to find what r is. So our r, using the quadratic formula, is -1 plus or minus square root of 5 over 2. And what we'll do to keep r positive is take the positive sign from the square root, and that gives us our very famous golden ratio. So in one slide, here is the magic of the golden section search, which I've said a few times, so you should get it by now. But here's iteration I, and here's the next iteration. So in the next iteration, we've closed in on one side of the previous iteration, but notice how the lines coincide. Our new lower limit is x1 from the previous iteration. Our x1, our new x1, is x2 from the previous iteration. And our upper limit is the upper limit from the previous iteration. We have a new x2, that's at a new point. That's the only one for this next iteration where we have to evaluate the function. And every iteration, we eliminate almost 40% of the total span. So that's pretty cool. We eliminate almost half of the span, and we only have to evaluate the function at one new point. If we didn't use that golden ratio, we'd have to evaluate it at least 2 more points. So we're doubling the number, we're doubling the time for this algorithm to converge. And again, keep yourself in the mindset that every time you evaluate this function, it takes about an hour. And very often real computation is that way because it's not really an equation you're using. That evaluation of the function could be a simulation or something else. It just takes a long time. So that's the golden section search.